Well, here we are, made it to part 6. So here we go. Contact. Must have something about that so the backlight don't come on until the screen's cleared. The projects never stop. Right. As you want to see how long it takes to go from cold to hot to soldering a component. So a capacitor all ready to go. So here we go. Irons off. Don't know how many seconds we got so far. But, I'm going to do a brilliant job. Just tack it on. Dirty bit of variboard. Really should clean your variboard before you use it. Well, there you go. How's that? I know it's a bit close, but it's a reasonable solder job. Yeah, it's working really well. And I'll throw in a picture in a second of what the pucker unit looks like. But I suppose now is to go on and describe what's living in here and what makes it an interesting project that we've all seen going together. Well, here we see a picture of the inside of the soldering iron. That's the body of where the tip plugs in. This is the ground, I think it is, and power lead going off for the tip heater. The tip sensor is amplified by a little op amp here, and this device here underneath the wires is the vibration sensor. Not really sure how that bit works. There's no markings on it. It looks a bit like a multi-layer ceramic capacitor, which is what I thought it was at first, but not quite sure what it is. And so, see here, it's a very narrow board. The wires just about fit when the tube's plugged in. Here we have the other side. As you can see, I draw on the pictures, and to remind me of what's where. So here you've got 5 volts, SDA, CLK, 0 volts over here. That's the heater power. Obviously that goes back to 0 volts. The first chip that the power comes to, or the not the power, say the data lines come to, is a hard one. I never did quite find out the exact part number, but it appears on the bus as something like a 24 LC memory or EEPROM. So it's obviously used to store settings. The original iron system, when you change the temperature of the iron, it would store it in the iron, so you could plug the iron back in and it would come back at the temperature it was last used at when you're changing between irons. The next chip here is a diode array. There's 4 diodes in there. There's a common pin that commons to the 4 diodes that go off to the 4 outer pins, and that's just a static chip. Any high voltages present on the bus get shorted down to 0 volts and protect the 2 chips either side. This chip here was labelled C58, you can't see because I've drawn on it, and after a lot of searching I eventually found that, and it is in fact a 4-channel ADC, and we'll be showing some information on that in a minute. after hunting around, trying to find a 8-pin chip that was marked C58 and was actually an ADC, because that's what it appeared to be doing. I came across the data sheet, and here we can see here there is a branding C58 and it is an AD 7995, 8 lead slot 203, so it matches, all of the descriptions match, and when you electrically, or when you talk to the chip electrically, it seems to match what's in this data sheet. As we can see here, this is the information, or part of the information. I just cut it out of the data sheet just to say that, you know, what the chip is. It is actually a 7995, which is a 10-bit 4-channel A to D. Yeah, you can run up to 11 block diagram. It just shows it's got the 4 inputs, where one of them can be the reference, and it has the logic, the I2C bus, power and ground. And I'm using it in the manner where the reference is taken from VDD. So, you know, I think on the board VIN3 might be tied to VDD anyway, so you probably use that if you want. But in how I'm using it, I'm just referencing it to the supply voltage. Yeah, you can run up to 11 megs, not going to run that fast. So that's the general description of the ADC. And the most important part of the data sheet is how you actually get the data out. So basically there is a register, and you just keep reading the register and it cycles through. The first 2 bits on the most significant are always 0. The second 2, D12 and 13, are the channel address, so it's either 00, 01, 10 or 11. And the low register, now the bottom 4 bits can mean many things. If you have the 12-bit ADC, they're all data. If you have the 10-bit ADC, they're zeros, they're data. And if you have the 8-bit ADC, they are all zeros. Whereas the 7995 is the 10-bit, so, you know, they're zeros. D2 to D11 is where our data lives. So when I read the data, all I have to do is strip out those 2 bits to work out which channel I'm dealing with, strip out the data, shift it down, shift it to the right 2, and yeah, there I have my channel and my value. That's what I do in the software. Well, I'll try and keep this short because there's a lot of software and it's not that complicated. So the main part is the main loop, which is basically just a switch statement, and the state is controlled externally by an interrupt timer, and so basically it spends most of its time in the idle state, which is processing the buttons, looking to see if any buttons need working on. The setup, pretty standard, you know, set up your pins, whether they're inputs, outputs, attach the interrupt to the pin 2, and we're looking for a button press and a rising voltage. And then we begin the TFT screen. We initialize the timer, we set the I2C clock, and we start the serial, and then we wait. At some point that's going to go, because obviously once it's running there's no need for a serial bus. And down here basically we have a setup screen grid command that just draws the basic grid pattern on the screen, and then there's some commands just to update the default values at startup. Here we can see the interrupt button pressed routine, and so basically if the diode signal from the three buttons goes high, the interrupt is called, it comes into here, and then basically what we're doing is we're stripping off all the bits that aren't relevant, so we've only got the 3 bits left for the button itself, and then we're right shifting them down so that it's a sort of number that starts at 0, and then we've just given them numbers. So the case statement, it just uses the result and falls through, into the right one, sets a flag as to what button's pressed, and that's all the interrupt one does. This is initializing the timer interrupt, and basically we're disabling all the interrupts while we go in and do it, and this code here is setting the timer up to give us a 5 millisecond interrupt. As you can see, this is the interrupt service routine for the timer, and the first thing it does is it preloads the counter back for the next interrupt, and we're basically looking to see what's going on. The iron power is a number between 0 and 5, 5 being maximum power, and basically what it does is if it is greater than 0, it goes in, and if the pin's low it sets it high, otherwise it sets it low, and then it decrements the power. So every 5 milliseconds the pin will go high, 5 milliseconds, then it will go low. Next 5 milliseconds it will go high again if there's a request, and then basically it decrements the iron power. So basically the maximum you can get from power to the iron is 5 bursts of 5 milliseconds each over a certain period, and then we just got a little loop counter in there that counts up, and every time it gets to a certain value it sets the state to read the ADC, as I've said earlier in the ADC, and a bit later on it gets a bit higher, it sets the state to be set power, and it clears the loop counter. And so it basically just goes read ADC, bit later set the power, come back, read ADC, bit later set the power. And then down the bottom we used to have 2 basic timers that are decremented every 5 milliseconds, and they are set from outside, and so basically they just give us a couple of timers based on a step size of 5 milliseconds. So this is the read ADC function. It begins a transmission to the ADC, it requests 8 bytes to read, waits for the end of it, and reads them out, and then basically puts the 2 bytes together and sends them out. Now these can be in where it says like channel 2, it's ADC 2 channel, you can't tell which one's on channel of the ADC it is. If there's a problem and it's been interrupted, they get out of sync, and so basically what happens is up here you've got the ADC 2 channel, it takes in the 16 bits and basically it masks out the 2 bits for the channel ID, shifts them to the right, which gives me a number of like 0 to 3, and then that's the channel, and then it does basically the same. It masks out the 10 bits data and then shifts it to the left to give me just the data, and then it's just a switch on the channel, and so that it puts the data in the right place for use later. Now this is the power display function, and it basically takes a number between like 1 and 5 or 0 and 5, and it's another switch statement, only this time there's no breaks in there. And so what happens is it comes in, it fills a rectangle to the background colour, so it overwrites and clears the power indications that's there, and then it just drops in at the number it's at. So if it's a 4, it comes in at case 4, and then it basically draws that rectangle, falls down to there, draws that one, falls down to there, draws that one, falls down to there, draws that one, then falls out. And so basically the higher the number, the more rectangles get drawn. So that's as simple as that. Right, this is the movement routine or function. I'm not going to go into it too much because even I get a bit confused with how I wrote it. And basically there's a flag set that if it's the first run, then the old movement is the new movement, so that there is no movement, and that stops it powering the iron up when it first turns on. And then basically what we're looking for is, has it moved? Is it greater than the trig point? If it is, then we've now detected the first movement, and movement is detected, and so we're going to go into the show. We put on the screen the show heating. Then, if we've had first movement and the idle timer is timed out, then it's just been sitting there heating and no movement. So basically we could change the screen to say show idle, and it drops down into the idle sort of setting, and then we have one where we've stopped running, it's sitting there not doing anything. So what we're going to do now is we're going to go down to standby, which is basically turn the heater off altogether. And so basically that's what it does. This is the update power function or routine, and basically it has two parts of it. The upper part is basically producing the error value, and that's based on the current iron temperature and the temperature you want. And so basically I've got if movement has been detected and the iron, start again. Beep. This is the update power routine. It has two parts. It has the kind of how to create the error and then what to do with the error. And basically, if the iron has moved and it is the first time and first movement has been detected, it sets the error to be the current iron temperature divided by the temperature that you want, and that gives you an error. If movement hasn't been detected but first movement has been detected, then obviously it's been hot but has stopped moving, and so now the iron temperature is compared to the idle temperature. So the iron will cool down to the temperature set by the idle temp. And then we have the last one, which basically is, it has been hot, it has been idled, it's now timed out from that, and so we'll compare it to the standby temp, which is basically like 0, and so the iron just cools right down to almost nothing, cools down to nothing. So that's the kind of 3 states the iron can be in. And then this is a bit crude. It's just got the error, and it's just based on some random, or not random, but some numbers for the error, size of the error. And so the kind of smaller the error, the less power the bigger the error, the more power. So max power is like number 5, and so big error, full power, and as the error shrinks, you know, it's max power -1, max power -2, max power -3, 4, and then basically that's about it. And so, you know, that's how that bit works. Very crude. It's not a PID controller of any sort, but it's working at the moment, and at some point I will replace that with a PID controller.